Everyone, welcome to the webinar series organized by the IUFRO Working Group on Tree Growth, Mortality, and Remote Sensing. Today we have as a presenter Dr. Andrew Hudak. He's a research forester at U.S. Forest Service in Moscow, Idaho, and he will be talking about fuel mapping with remote sensing. Uh, Please mute your. Okay. Um, as I was saying, today we have Dr. Andrew Hudak. He will be talking about fuel mapping at different scales with remote sensing. But before I pass Dr. Hudak the stage, I want to mention that we are part of the International Union of Forest Research Organizations, IUFRO. That IUFRO is wait, that IUFRO's mission is to advance research excellence and knowledge sharing and foster the development of science-based solutions to forest-related challenges for the benefit of forests and the people worldwide, and that the core values of IUFRO are the excellence, networking, diversity, and integrity. So I'm going to stop sharing and pass the stage to Dr. Hudak, and I hope you enjoy the webinar.
Thank you, Paco. I really appreciate the invitation and the opportunity to present to you today. Oh, looks like someone may not be muted.
Okay, let me.
No, te pedía un nombre para entrar a la red.
Please mute your microphones.
Okay. Yes, so thank you for this opportunity to present today. I attended one of these before several months ago. I remember Nick Crookston presented, and I remember not just a good talk, but a friendly audience, and there was some nice discussion that followed. So I'm hoping for the same today, of some nice discussion. The topic today is fuel mapping, and what I've been involved with in the last few years across different scales of fuel mapping, all of which involve some type of remote sensing data, but also some type of field measurements as well that we're associating with the remote sensing data. And that's an important point because it's the physical fuel measurements on the ground that we care about and we're trying to predict. And where we're pushing the envelope is trying to map these physical fuel attributes at different scales using remote sensing data. So there's actually more contributors than I've listed here to the ideas and the results that I'll be presenting here today. But this is a partial list of some of the figures and such that I'm directly showing you today. This morning for me, this afternoon for you. The work, and I should acknowledge the funders, the CERTA program, which is the DoD's Strategic Environmental Research and Development Program, has funded a lot of this work that I'll present today. The Joint Forest Science Program has also, this is an interagency, federal agency program that's funded myself and Paco here. And NASA has also provided considerable funding for larger scale mapping. So my outline today is just first give you kind of an overview of some of the ideas that have emerged on this topic of fuel mapping at different scales. And then I like results-oriented talks, so I'm going to give you an example of how we do fuel estimation by what I'm calling a direct approach, where we associate those physical fuel measurements collected in the field with remote sensing data. And then I'll give you an example of an indirect approach of fuels estimation for estimating surface and ground fuels. And then finally, most recent work, very new actually, not even, it's a manuscript in prep, for transferring some of these ideas and scaling them to another site for both direct and indirect fuel estimation. Okay, so there's several sort of perceived tension points with fuel mapping. One of them is that some people like to go top down, some people like to go bottom up. And I've had my preferences myself. I tended to be a bottom up person. But with time, I've also recognized the value of top down. And I really think we need them both. Mapping fuels is challenging. And so I think we actually need to come at it from both directions. From the top down, this is broader scale fuel mapping where we're using regional or national data sets. And these could be field data sets or remote sensing data set. A couple things that you may not have heard of that we have in the US, one is fast fuels. This is a voxelation to predict fuel attributes across the whole country, and it's based on an imputed map of tree list. So it doesn't actually give you spatially aware estimates of where the trees are at a pixel scale, but it gives you an imputed tree list from the National Forest Inventory data, which in the US is called FIA, Forest Inventory and Analysis Program. So those plots are our National Forest Inventory, and there's an imputed map of tree list across the country, and that's what's been linked to fast fuels to provide a map. There's also surface fuel maps, primarily put out there by the Wildfire program. And these tend to be categorical maps where you have fuel bed classes or categories, but there's actually dozens, if not hundreds, of these landfire fuel bed types. And that's the kind of the state of the art or operational space now for surface fuel mapping. And this type of information, we want them at a finer scale because it's at the finer scales that fire behavior models operate. And so this gets now to the bottom-up approach. We want to be able to simulate fire behavior with physics-based models, and at the fine scale, they very much depend on fuel distributions and fuel variation. So we need methods to capture that structural variability of fuels at the very fine scale. And we know from previous studies that they really do vary at fine scales. So QuickFire is the kind of the leading physics-based fire model now that is kind of on the cusp of operational utility because it can work at the scale of a large prescribed burn. And that then gives it some utility to managers. But what distinguishes these physics-based models is that they capture the 3D fuel variation and they know where the trees are, and that affects the wind flow. And they also account for topography. So I'm not going to show you a fire behavior triangle, but fuels, fire weather, and topography are the three determinants of fire behavior. And it's only the physics-based models that capture that variation as well as the interactions between those variables. Okay, so here's a little video of a quick-fire simulation through a forest stand on a hill slope. And it's these kinds of simulations that managers use to test different scenarios of fuel moisture, different fuel distributions, and how that will affect the resulting fire behavior. So this is kind of the goal of some of this fine scale fuel mapping, to provide inputs, 3D inputs to these types of models. Another application is fuel moisture mapping. And this is something I've not been involved with myself, but I do want to point to it because It's perceived by many in the fuels world as kind of the holy grail of modeling and mapping and measurements, bringing them all together to model fuel moisture dynamics, because it's a very difficult problem. It varies so much spatially at a fine scale because of the fuel distributions and fine scale patterns of shadowing. And you can see in this video on the left how the solar angle throughout the course of the day changes. It changes the shading patterns from the tree crowns, and that affects the fuel moisture at fine scales. At a larger scale, there's other variables that matter, such as the topographic condition, the spectral variability, which depends on species composition, elevation slope aspect, and these kind of things. These all have a role in fuel moisture dynamics. And fuel moisture is so important because that is a big determinant of whether or not you can do a prescribed fire. And in wildfire cases where it's too dry to burn prescribed fires, but you have fire danger from wildfires, the amount of fuel moisture really is a primary determinant about how hazardous conditions are at a given point in time. And even in the course of a day, you know, mid-afternoon has lower fuel moistures than first thing in the morning, and that has a big effect on fire behavior. So this is sort of like an aspirational goal for why we need fuel mapping at a fine scale and scaled up to larger scales too, to capture these dynamics. I'm going to focus more on the fine scale today, because that really is a scale where fuels vary, and that's the fundamental variation that we're trying to capture, not only to feed these physics-based fire models, but then to try to scale up these estimates to more operational scales where managers make decisions. So the cutting edge, I would say, for fuel measurements, physical fuel measurements, is a 3D fuels project that was led by Susan Pritchard. This was funded by that CERTIP program. And they went in the field and they painstakingly measured the fuel properties, including some things like particle density, the bulk density of fuels, surface area to volume ratio, leaf shape and thickness. These are just some of the physical fuel properties that determine fire behavior. And the data were collected at a very fine scale and with high geolocation accuracy. Now you see this depiction of voxels in the upper right. These are nested voxels, and so you can summarize what they try to do is summarize these physical fuel properties at this voxel scale. So they sampled not only horizontally in space with their field plots and in microplots, but they had vertical stratification of the field samples, so they could look at changes of, say, for example, bulk density with height above the ground, because it tends to be much, much higher very near the ground than aloft. So they're working on, they have a library of intrinsic fuel properties here. This is an older one that has a website already. The other one, which is called the 3D Fuels Repository, is just about ready to go live, and it'll have some of these other physical fuel properties. They also collected TLS scans where all these plots were. And so they have the non-destructive data, the point cloud data, with which to associate to the physical fuel measurements. So a big part of 3D Fuels project is looking at those associations between physical fuel properties and TLS metrics. Here's like a step that's another project that's been kind of born out of that 3D Fuels. It's called the Fuels Craft project. And in this project, they're simulating fuel bed. So, you know, you can go out and measure fuel properties at a fine scale, but it's painstaking work. And you can only do very small plots. You know, there's too much out there. And so we need remote sensing, not only to capture the fine scale variability, but also to scale up. And even just cell phone photos, like there on the right, are some depictions of different fuel beds that have been simulated from cell phone images, 3D cell phone images. And the idea here is to capture that spatial variability and the variability in composition of these different fuel beds with the photos. So you have both structural and spectral information. And then when you have those fine scale objects defined, then you can link that to the 3D fuels property to assign physical attributes to these different fuel bed components. And then at the larger scale, this is actually an AI image. It kind of looks AI, this image, but it's just to kind of make the point that we can scale up these simulated fuel beds to a more operational scale by linking them, associating them with the tree distributions through imputation or other approaches. I want to point out a useful package that you may not be aware of if you're interested in pursuing fuels research and doing some of these scaling operations. It's called the Cloud to Trees package in R, developed by Wade Tinkham. And it's very good at translating, say, rasters of a physical fuel attribute at some scale to tree crown objects or other objects. And so it could translate between pixels and voxels, tree crowns, and rasterized or voxelized arrays of the fuel attributes. And this is another perceived tension point. Some people think, well, we just need to do everything in a raster or a voxel environment, a regular array of estimates. And that's actually what the fire behavior models need, is that sort of input. But when you actually look at fuels and how they vary in the field, objects are a better sort of conceptual model for capturing how fuels vary, because fuels tend to be very clumped. Of course, canopy fuels are clumped at the scale of individual tree crowns or clumps of trees. And similarly, shrubs on the ground, grass, and it tends to be very patchy. So objects also have an important role in how we capture fuels variability and model it. But it's not an either or proposition. We don't need to just focus on one or the other. We actually need both. And we need tools like this to be able to translate between regular arrays of pixels and voxels in 2D and 3D, or objects. And objects can also be 2D or 3D. You can have 2D polygon objects on the ground, which depends like a projected crown area in 2D space, or you can have like a convex hull type sort of 3D rendering of a tree crown. So we need also measurements and models. There's a role for both. I'm a measurements guy myself, so I feel like if we can measure something, we should use measurements to the extent we can, but things that we can't measure easily, for example, fuel moisture, as I was just talking about, we really need models too. So we can take measurements, and remote sensing is an important source of those kinds of measurements, but so is the physical fuel measurements on the ground. We need those as inputs into models. And we do this at both coarse scales of observation and fine scales. At the fine scale, I've mentioned TLS, but there's also mobile laser scanning and handheld photogrammetry that I've mentioned. There's also UAS, which is sort of at a slightly larger scale, bridging up to the airborne LiDAR scanning scale. And I'm an airborne LiDAR guy myself. I see that as a really important scale for bridging the gap between fine scale fuel properties and then coarser scale patterns, such as what we capture with satellite imagery. I also want to cite on the measurement side some important databases at the larger regional scale. So I mentioned the 3D Fuels project already. There's another project called Intellimon where they're sampling fuel conditions across the country and scanning them as well. So it sort of grew out of the 3D Fuels sort of philosophy. And then there's the FIA program, which I mentioned. That's the National Forest Inventory Program, where they actually collect fuel measurements as well on the systematic plots across the country. So we need to leverage that data. Here's just a picture, a screenshot from the website of Intellimon, and it's not real up to date now, but it gives you a sense for the distribution of fuel sampling on the ground, mostly in the southern tier of the US, but also where they've collected TLS data. So they can make these associations between physical measurements and TLS metrics. But we need to scale these up, and it's the airborne LiDAR scale that I think is key for doing that. So the US is now approaching national LiDAR coverage. And this is a recent map that I downloaded from the USGS site. The darker green shows higher quality, higher data density LiDAR collections. Those tend to correspond to forested areas or floodplain mapping. The lighter green is what we call QL2, and it's not as dense, but they also tend to be not as densely forested. So you don't need the same point density to achieve good ground elevation data, because it's ground elevation data that's sort of driving this national effort to get national LiDAR coverage. Having a 1 meter DTM across the whole country is a goal, but it's providing these data sets to pursue other applications too, such as the forestry and fuel applications that we're using these data sets for. So I won't get into a NASA project, but we're mapping forest and fuel attributes across the West from these airborne LiDAR data sets. And what we need then is a strategy for associating the airborne LiDAR with the TLS scans. So I pulled this example out from Juan Castarena's work. He has automated a program to match TLS scans with ALS scans at this scale of the TLS scans. The airborne LiDAR tends to be delivered in georectified, orthometrically correct coordinates in real world coordinates. The TLS data are not collected typically in real world coordinates. So, and there's always an offset. So the idea is to co-register the TLS scans to match the ALS scans. And it's the distribution of treetops that provides the tie points for the software to do that. So here's a top-down view of a large plot with ALS scans depicted in yellow, and then some plots within with TLS scans, and the software co-registers these point clouds. It's actually an important step because there's always a little bit of an offset, and it tends to be about a meter or two. Here's an example of the offset between ALS and a UAS LiDAR collection. Here we're calling it ULS, unoccupied laser scanning, but it's from a drone, and we observed this offset in this Sican Marsh study area that I'll talk about more later. That's a problem because even a 1 or 2 meter difference between the registration of these two data sets can break the correlations at the tree scale. Trees vary, and so if you move your frame of reference 1 or 2 meters, you get a very different estimate. So it's important to match these together to have successful scaling between fine scale and what I'll call this moderate scale of the whole stand. And in this case, this was the offset. It was actually 2.8 meters in X and almost a meter in Y. So Okay, next part of my talk now is, as per my outline, is just presenting a direct fuel modeling strategy. This, I'm going to use TLS as an example here, focusing on that fine scale. But this sort of modeling approach can be applied to mobile laser scanning or airborne laser scanning. It scales between all these different point cloud data sets. It could also be applied to UAS point clouds or photogrammetric point clouds, although you have to be cautious because you don't get the same penetration through the canopy as you do with LiDAR. So the basic approach is you have your field sample data of the physical fuel attribute. I tend to focus on the loading, so that's the kilograms of fuel per meter squared. And then you have to associate it with your point cloud data, in this case TLS, and you have a variety of metrics for predictive modeling that you calculate from the point cloud. So those are your predictor variables with which you use those to fit a model. So you do some sort of variable selection procedure. So you don't use all the metrics because there's too many and we want to have a parsimonious model. So we do some sort of variable selection and we feed that into a predictive model like random forest, which is something we use a lot. But you could also use regression, imputation, other methods. And then there may or may not be some additional validation that you do with the model results. And then once you have a model you like, then you apply it to those same LiDAR metrics that were selected by the model to generate a map. On the left is sort of a depiction of a fine scale model fitting operation based on TLS data. The surface fuel attributes near the ground is mostly the litter layer depicted in brown. And this is a palmetto here, which we often find in Florida. And I'll be talking more about that in an example. And then here is the point cloud depiction of that palmetto. And notice how the TLS does a much better job of capturing this erectophile, this aloft portion of the fuels above ground than it does below ground. And this is the problem of occlusion. And all LiDAR suffers from this, airborne, MLS, TLS. So that's something that will impact our modeling, as you'll see. So this example I'm going to show you was done at the Osceola Experimental Forest site in northern Florida. And what's appealing about this site is it's a long-term fire experiment. It's been going on since 1958, where they've done a randomized block design, as shown in the map on the left. And since 1958, they've been burning within these 100 by 100 meter blocks. Actually, it's probably 100 yard by 100 yard, because back then they would not have been thinking metric at all. But approximately 1 hectare experimental blocks, and they maintain them at either a 1-year fire return interval, 2 years, 4 years, or they haven't burned them at all. And then in the map in the middle, you see, let's see, it's 9 of these units, of these burn units that we instrumented on the ground and measured fuel properties in these fine scale plots. And that's what the black squares represent, are the plots that were put across these different experimental burn units. And then we scanned the plots with TLS. We actually drove the TLS in the back of a pickup truck along all of the fire lines that bisect between these different experimental units, so we could scan from a higher vantage point. And not only that, I rented a boom lift, and we could go around the outer perimeter of this study area from a much higher vantage point. And it wasn't as high as the treetops. It was, as sort of this cartoon depiction suggests, it was actually up to about the crown base height, which is about, maybe 15 meters above the ground. No, 10 meters. Let's say 10 meters above the ground. So you're minimizing the occlusion from the overstory, but you still have sort of this high oblique angle. But the idea was, from this high vantage point, you would get better penetration into the surface fuel bed, because that's what we're really trying to map. These burns are surface fires. They're prescribed fires. They actually used to maintain forest health, so they don't hurt the trees. The trees are adapted to the frequent frequent low intensity burns. And then analytically, what we did is, from the TLS point clouds, we removed the trees, the crowns and the tree boles, and we focused the modeling on this surface fuel bed layer, which is shrubs, palmetto, grasses, and needlecast. So we did this association between the physical fuel measurements at those small plots and the TLS metrics, and we got good model fits. I mean, if here are the model fit statistics for 8 different response variables summarized from the field data. So either total biomass, or just the fine fuels, or just the fine woody debris, or even just the 1-hour fuels or the 10-hour fuels. Or just the pine needles. We sliced and diced the physical fuel measurements and fit separate models to try to predict each fuel component. And we got good R squares. I'll just jump to the right. You know, we get decent R squared statistics. And then if you look at the predicted versus observed relationships for these same 8 response variables, they all look good, really. So initially, you know, we were happy. It's like, wow, this is working just fine. But I have to caution you, because when you actually dig a little bit deeper, a problem emerges, and that's the metrics that are selected are very similar between all these different models. And if you look at the importance values that Random Forest provides in these metrics that were selected, it's very similar patterns, where the P second and the P third, like at the top of these lists, this is the percentage of returns at height intervals near the ground. So P second is very near the ground. P3 is just the vertical stratum just above that. And that makes sense, because it's that density of returns very near the ground that correlates the highest with the fuel loading, which is primarily driven by the needle deposition from the overstory. So that's fuel very near the ground. So the problem here is we're not getting differentiation. And you can also see that when you look at the differences between fire return intervals. We know from the measurements on the ground that fuels accumulate. So you'll find almost twice as much fuel in a 2-year fire return interval unit as you would a 1-year, because there's been an additional year for the fuel to accumulate, mostly from the overstory deposition. And then similarly, 4 years later, there's that much more fuel on the ground. However, we're not seeing that differentiation here in the fuel loading estimates for any of these 8 response variables. And indeed, if you map it across the units, the patterns are very similar regardless of the fire return interval. We should be seeing more fuel in the 4-year fire return interval than we are in the 2-year, or especially the 1-year. So it's capturing the horizontal variability quite well, and the erectile stuff that has a role in estimating these attributes that we predicted, but it's not getting depth, especially depth very near the ground where most of the fuel is. So this sort of lays the groundwork for tackling it using an indirect approach. As I said earlier, if you can't measure it, then you have to model it. So our direct modeling method for this site, was not producing satisfactory results. So we went indirect, and this is the work that Nuria Sanchez has been doing for several years now. So we actually go direct for getting canopy fuels, and we use the LiDAR to characterize the amount of biomass in the overstory, and we can partition that into the foliage, branch and stem biomass or bowl biomass. But then for the indirect approach, we have to model the deposition of that material to the forest floor to get surface fuel load estimates. And we also need to know what is the decomposition rate, because if you don't burn it, then that material decomposes. And you need to know time since fire, especially in this frequently burned environment, which has such an overriding influence on the fuel load. In this paper that she just got accepted a couple months ago, she also simulated duff development. So not only are we predicting the surface fuel bed loadings indirectly, we are simulating duff development for these different fire return intervals. And that's using a model developed in Finland called the ISO 20. And it models different soil organic matter pools that comprise the duff layer. Duff is the equivalent of ground fuels, and it's what those in the fire community call ground fuel. Call it duff, or you could call it the O horizon or the organic soil horizon. So it takes temperature and moisture inputs for modeling those dynamics. And then the assumption for relating these 4 different variables of deposition, decomposition, time since fire, and composition is Olson's model. So this shows you how the fuel accumulation asymptotes over time. And in this environment with frequent burning, we're kind of in the steep part of that curve where there's a lot of change in the litter accumulation over just the first few years. So here's NURIA's results. You've seen the map of the layout of the units already. On the right is the canopy height model, and this just shows how the trees really aren't varying very much between these different experimental burn units. And then we have to model these different variables. We need to model the fuel production rates. So this is what the data we use, the data collected on the ground, is for informing the duff simulation model. We need to know about the fine root turnover as well. So it's actually fine roots in that duff layer that turn over very quickly and provide a lot of the inputs into duff development. But then after that is the tree leaf litter and other material, other litter, and then the fine-wooded debris, coarse-wooded debris, and coarse roots are minor components of the duff development. For this modeling approach, we need to parameterize it with turnover rates, which is much faster for the needles and leaves than it is for the finer branches or coarse branches. And we need to know consumption rates when it does burn. And you tend to burn more of that fine material, like the leaf litter, than you do the coarser fractions. And the duff especially, very little of the duff is burned in a prescribed fire window. If it's too dry, they won't burn. And now we get maps that are much more reasonable. So in the left is the biomass production map. That tends to be pretty evenly distributed, just as a function of where the trees are. The duff loading map, I'm sorry, that is mislabeled. That's actually an annual accumulation, and it just got copied and pasted from the map on the right. But the map on the right is the actual accumulated load over time. And you can see how much more duff there is in the unburned units. So the model is capturing that continual accumulation of and decomposition of litter material into the duff, and we get much higher duff loads there. But it's also higher in the 4-year rough than the 2-year rough, and lowest in the 1-year rough. So modeling by this indirect approach is working to capture this the dynamics in the different fire return intervals. So here is the model, simulated model results, looking at the duff component per burn unit. You can see how the unburned accumulates over this 65+ year history now of this experiment. And it's the 1-year fire return interval where you have actual diminishing duff over time. And that's what we see in the field too. It's very hard to find duff in the 1-year fire return interval. It's the 4-year that sort of is closest to an equilibrium condition. And that kind of approximates actually what's believed to be the historical fire regime for this type of forest. Then we compared the simulated duff loads here on the x-axis compared to the measurements on the ground across these different experimental burn units. And we got a good relationship with minimal bias. So this works well in the southeastern US in a frequent fire system. Can we now transfer it to the western US? And so now this gets into the last portion of my talk. Our study area in this case is Sican Marsh, and this is a nature conservancy preserve in south central Oregon. And it was impacted by the Bootleg fire in 2021. This was at the time the largest wildfire in Oregon state history. And it burned a huge area. I don't remember how many thousands of hectares it burned. But the Sican Marsh study area is just this black rectangle up here. And this is a zoom in shot of a black rectangle along with a couple other parcels below. And these kind of strange study area boundary is defined by the 2018 LiDAR that was collected for this area. And that's what we're using to capture the pre-fire fuel conditions in the canopy. We went and sampled this area, stratifying by whether or not it was burned in the Bootleg fire, whether or not it had been previously treated with either mechanical treatments or prescribed fires, or not treated or burned at all. So it's 48 plots by that stratified random design. And note also that this study area, if I go back to the burn severity map in the lower left, this is a randomized burn ratio map, relativized burn ratio map, one of the metrics or indices for burn severity. It's largely green, and that's because the TNC did all these fuel treatments before the Bootleg wildfire came along. And the treatments did a very good job of mitigating the severe fire effects. So we have a nice distribution of low, moderate, and high severity. That was another reason this was an appealing area to study. So we distributed these 48 plots across, stratified by the treatment types, as I just described, but then we didn't stratify in bird severity, but we got like a decent distribution of plots across all severity classes. The fewest in the high and the most in the unburned by our sampling approach, but that actually works well for this study because we're trying to capture fuel development and fuel deposition, and the variability in fuels tends to be higher in low burn severity than in moderate, and the lowest in high, which tends to have a more homogenizing influence on fuel distributions. And the unburned would be the most variable. Where you have higher fuel loads, you also have the higher fuel variability, is a more succinct way of saying that. So Nuria did this pretty much the same approach as she did at Osceola, where she segmented out the individual tree crowns and modeled the tree crown foliage biomass, branch biomass, and bulb biomass. And for this analysis, we focused on this variable called canopy fuel load, CFL. So on the left is crown fuel load. So CFL is crown fuel load, and you can see that most of that map in the upper left is green because the tree crowns survived. The treatment units mitigated the Bootleg fire severity to become a surface fire. But there is an area of high severity, which is kind of this orangish area in the middle left of that map. You can also summarize the data as the percent change between the pre and post fire LiDAR collections, which is the change in crown fuel load there on the right, which is higher in the high severity area. And then down at the bottom of this map in this high severity area, most of the tree crowns were consumed. And so that's why they're colored red. And then a lesser number were just scorched, and that's why they're colored orange. But we also tested an area-based approach where we trained the random forest model to predict similar response variables, but at the canopy scale rather than the tree crown level. Because ultimately we want an input into fire behavior models that's rasterized. And we thought, well, a large source of uncertainty with the segmented tree crown approach is just the segmentation and not accurately capturing the tree crowns. With the area-based approach, by summarizing the field data at the plot scale and training a random forest model, we actually can go straight to pixels. And FB in this case is foliage biomass. So this is the response variable that we're mapping here. But you see similar patterns in severity. Well, the tree crown approach on the left is actually not as good as the canopy, the area-based approach with the 6 graphs on the right. And so this was actually good news to us. The individual graphs show FB is foliage biomass, BB is branch biomass, and BOL is the bole biomass. And in the, and then the colors, the colors indicate the breakdown of burn severity across these different models. But they were not parameterized to predict those separately. That's just the distribution as they were called in the field. That's not influencing the model here. So we have less bias in the area-based approach for predicting these attributes. So in this case, the area-based approach worked better than the crown scale approach. And this is good news because it's more scalable and you don't have to bother with the segmentation. So once doing that with the direct approach, now we went indirect for the surface fuel loads. And so the surface fuel estimates are these maps here based on either the object-based, the tree crown level model, or the area-based model on the right. And then the patterns are very similar. Here again, when you compare, in this case, the litter estimates on the x-axis by this indirect approach to what we observed on the ground, there's less bias, or more proportionality, I should say, in the area-based approach, where it's closer to the one-to-one line. And this is the kind of bias that is a systematic bias that we think we could correct by just tweaking the model, where we're just slightly underestimating the litter loads by the area-based approach. But that proportionality is good news for scalability. Okay, and we want to couple the surface fuels to the overstory, and that's what we've done here. And kind of the motivation for doing that is just like in fire behavior, the way you get from a surface fire to a crown fire depends on fuel, topography, and fire weather conditions, but we know they're coupled. And we need to understand the surface fire behavior to be able to then scale it up to the crown fire. It's very similar with the fuel question. The fuel distributions of the surface fuels is very important for determining that surface fire behavior. So, but that's what we're doing, where we need to improve in our fuel modeling is that surface fuel layer. And that's the reason we've been focused on that. And that's the reason we're going indirect. I did have a couple more slides, but I'm going to stop there, I think, because I don't want to shortchange the discussion time.
Okay, Andy, thank you very much for the presentation. So we have about 10 minutes for questions. There is one already in the chat. Veronica, she was asking if 4 meters fuel mapping is too detailed to be used in fire behavior modeling. And she was also asking about I think it's the
Maybe foliage
fuel.
biomass?
I think it was the fuel database, the fuel properties database that you showed at the beginning of the presentation.
Okay. Yeah, 4 meters is not too fine. In fact, this quick-fire model that the fire modelers are pretty focused on right now uses a 2-meter
Mhm.
resolution. And 1 meter is even better. So we're working on ways to downscale course to scale estimates that we get from our area-based model. NURIA has been predicting that at 10 meters, but now we're downscaling to higher resolution, and we're going back to the point cloud data to do that, or using the canopy height model. But yeah, it varies at that kind of scale, and that's why that 1 to 2 meter scale, which is kind of the offset you often observe between a fine scale TLS collection and ALS, why it's important to get that co-registered to tighten up those relationships. FBM, I suspect that means foliage biomass. And for the platform, so we are predicting that from airborne LiDAR data, but we can also predict it from TLS. And the Osceola example was TLS data collected from the boom lift. At SciCan, it's airborne LiDAR. We do have a UAS collection, but it's not over that whole study area. It's just a smaller area where we did a prescribed burn the year following the bootleg fire.
So when Veronica asked Andy, I recorded the time, and the question was when you were talking about these physical properties of fuels and the two databases at the beginning of the
Okay.
of the talk, and you show the map with some uh, measurements, mostly in the south and southwest. So I think that is the system she's
Okay,
asking about.
sorry. Yeah, the timestamp is revealing. So the 3D Fuels project, they had this sort of nested sampling design where they had microplots, which were actually half by half meter, and they sampled vertically. So those are precisely georectified. But then, as I mentioned, you have to calculate the offset if you're going to associate it with the TLS scans. The TLS scans were collected surrounding that plot to try to minimize occlusion from like a minimum of 3 view angles. But then there was a larger TLS scanning of a 200 by 200 meter area. So the number of small plots within that 200 by 200 meter block was, I want to say, perhaps 16, but it might have been even more. It might have been like 5 by 5 small plots within the 200 by 200 meter area. So the idea was to be able to scale up the fine scale to a TLS scale and have the TLS at that broader scale overlapping with the ALS scale. And then there was also an intention to associate those types of models with the ALS for further scaling. I don't,
So
does that help?
I think so.
Okay.
If someone has more questions, you can use the chat. And I have one question, and uh, my question is, what do you think is going to be or in 15 years of all the problems that you have talked about, which ones do you think will be solved or that we will progress far, and which one do you think are more challenging?
Yeah, good question. Well, I like to think that we're going to get far on the fuel loading question because I'm pretty focused on that. And so I would like to make progress on that one. I think we have the data and the methods now, the modeling methods to do it. Fuel moisture, I would put at the other end of the achievability scale in a, in a near time frame. I think that's going to continue to be tough, just because it's so dynamic. It's a constantly moving target, and it varies so much at fine spatial and temporal scales. But like people are talking a lot about this NISAR satellite, where it has a 12-day repeat. It's a L-band radar, and L-band can penetrate forest canopies better than C-band or other bands, and we think that'll be more sensitive to fuels variation. But also, it's going to be sensitive to fuel moisture because that affects the radar signal. So at that 12-day repeat, that's a pretty useful scale for capturing fuel moisture dynamics. Not diurnal dynamics. I think that we can continue to model, but sort of like the longer term change with seasonality and rainfall variability and drought and that sort of thing.
There's another question in the chat, which is on what methods can improve the ground level fuel detection using ground-based LiDAR in forests with dense canopy and understory?
Yeah, so the denser the forest, or especially the understory, the more the occlusion problem rears its ugly head. So MLS is one strategy. So by walking around with the LiDAR at the plot scale, you can capture data. It's not as resolute as TLS, but the view angles, it's sort of like this infinite number of view angles. And so you can get sort of merged scans that are less biased from those anisotropies from occlusion, where the trees are and where all the obstructing material is. But then, as you still get denser, you can't even walk through those canopies. So there, I think we have to rely more on airborne. And airborne is also suffering from occlusion, but we can model that to some extent using, I've used an assumption of the occlusion is proportional to the canopy cover. So the degree to which the surface fuel estimates are biased due to occlusion is a function of that overstory canopy cover. So you can assume it's underestimated and increase the estimation in proportion to the canopy cover. You can also apply a similar approach using the Beer-Lambert law of light extinction through a canopy. But also have to like promote again the indirect approach. Just characterize the overstory and then model the surface fuel development, because we just don't have a good signal, even with LiDAR, of the surface fuel conditions. So we have to model it.
I've got a question here in a different direction. Are you also considering microclimatic data like surface temperature, moisture, and so on in your models?
I'm not, but then I'm not doing the fuel moisture modeling. The people who are working on that are considering that microclimate. So that's capturing topographic gradients that impose some variability at a finer scale than is captured in the kind of the regional scale climate metrics. And then at the finest scale, you can try to capture the same, like that slide I showed of the video with the changing sun angle. So that's sort of like geometrical optical type modeling to model photons moving through the canopy, and when they go all the way to the surface and that sort of idea. So it's the LiDAR data that's allowing that sort of modeling to happen. We're using measurements to inform that kind of model. But yes, the idea there is we're capturing microclimate to some extent. I don't actually know though if they're trying to, I haven't seen a map at that scale of like what is the moisture or what is the temperature. So
Thanks.
yeah.
I have another question here in the chat. Have you seen anyone using cell phone LiDAR and spectral capabilities?
I've just heard about it anecdotally. I mentioned cell phones for those like sort of like stereo pair photos for simulated fuel beds. So you can get those from cell phones, but then you're talking about like the LiDAR that's on cell phones. And yeah, I think it may not be up to the task, because if I understand how that works, it's giving you some distance measurements, but it's kind of almost like more of a profiler than it is a scanning LiDAR. So it's not returning a point cloud. And I think you really need that to capture the spatial structure of the fuel.
Well, it's already 6. So we have well, it's time for the webinar. So please join me in an applause to Dr. Hudak and saying thank you to him. It was a very good presentation, and I'm glad that he came to the webinar series of the tree growth um, and mortality and remote sensing group, because forest fires are one of the main causes of mortality. So thank you very much. And well, I don't see the button for the applause, but
I saw some applause hands, so thank you very much. Again, thanks for the invitation.
Thank you for this very interesting and informative talk. It was very, very informative and very, very many good questions in the chat. Thanks a lot. And with it,
All right. Have a nice evening.
have a nice evening. Have a good day. And hopefully see you at the next webinar. Thank you.
thank you.
Yes, Paco, please add me to your mailing list so I can track when
I
webinars
will.
happen. Okay.
To the mailing list of the IUFRO webinars, or
Yeah.
I will.
Okay.
See you.
Bye.
Bye.
Bye bye.